Hello guys, welcome to this new channel. Am I audible? To check myself. Yeah, I guess I'm audible. That's it. I just want to know that. So, what's up, everyone? Myself, Karlapalam Trishikesh Krishna Sahan. Myself Sahan. I'm a second year student studying in Newton School of Technology. I'm here to learn many things, like not only right now I'm doing DSA series where I want to learn DSA. I need to learn DSA for myself, and I'm gonna be doing React.js. I'm gonna be doing JavaScript. I'm gonna be doing some N8 stuff. It's gonna be very interesting. I'm here to learn a lot, and also right now it's a morning stream, so football is not happening. But whenever the football happening, I will put the score for football enthusiasts so that they could also watch football with us. And yeah, that's it. I want to start DSA right here. Actually, if you see the title, I have said bubble sort, linked list, stacks and queue. It is because I've actually started DSA 2 days back. I've started with learning why do we need DSA, these kind of stuff, and then I've started learning about arrays. Then I've started with binary search, which is very important. Before binary search, I did time complexity and space complexity, which is very important for the DSA. It gives you the idea of optimization, and not only that, I have also started binary search, and I've did questions from binary search. So today it's time for bubble sort. Actually, I learned bubble sort, but now I need to implement the bubble sort. So I'm in the implementing stage. So I'll tell you straight away. I'm here to learn. I don't know things, so I'm going to be taking help of ChatGPT. I will be taking the help of ChatGPT, and also I will be taking help of YouTube and W3 schools, where I'll see some code and I'll try to learn, implement the things. And as suggest, ChatGPT is here, is not completely helping me with the code. It's actually giving me the challenge, so it gives me the structure and I have to build from the structure. So it's going to be awesome. Yeah, I think this is the best part of it. So I think it's better to start now. Then let's go. Let's start now with binary search. I'm going to be doing it. Binary search. So I will be here listening music when I'm doing. So I'm going to mute so that I would not get any copyright issues. I don't know in live we get copyright issues or not, but I have to make sure that. I think it's better to start now. Before that, let me check audio again, then I'm gonna start. But I have to make sure that. I think it's better to start. Before that, let me check audio again, then I'm gonna start. Check audio again, then I'm gonna start. Check audio again, then. Okay, now let's start with binary search. I'm gonna start with the binary search, so let's go. Sorry, I've completed binary search. As you can see, there are many types of binary search that I've did. First occurrence using recursion, blah blah blah. Now it's time for bubble sort. Let me do bubble sort. So bubble sort. Time complexity basically O of n square, because we are running 2 for loops in it. So I'll add a function define in which it contains array, an array in which it contains to sort we need array. I think that's more than it. We need array. That's it. So why I'm doing this, because I want to write in a function that I can store. So in this function, let me start. So I have a list which, let's say we have given the length of array also, so we know the length of array. Now let's start. What I'm gonna do here is I have to learn 2 loops around it. So I have to do 2 loops. So what I'm gonna do, let's first see the implementation, then we're gonna do. So first we have the length of the list. We're gonna generate 2 loops and we will write the code. So it's very simple. First, what we're gonna do is, for I in range, n, which is the length of an array, which are already given in the bubble sort function. So in the range n, so we're gonna go till n, till length of the array. Then for j in range n minus 1 minus I, because we have two attributes. So I think this is the perfect way to write the code. Yeah. So we are taking another further. We have to go with this. Then let's write the actual code. So the actual code, what exactly says, if ARR is greater than, if it's greater than ARR j, then what we're gonna do, we're gonna swap. How we gonna swap? ARR I comma ARR j, it becomes ARR j comma ARR I. This is, I think this is the easiest way to put the code, right? Then we need to print in the list. I think this is the best way to put it. I mean, this one. Then we need to return so let's give this code to ChatGPT. let's ask ChatGPT how this is gonna work. Okay, there is something mistake that I did with swap as the category says. You wrote, yeah, that's what I wrote. I is equal to 0. I've written the same thing, but what it is trying to say. So sorry, here I have written DSA. Yeah, my mistake. Now I think this is going to make sense for this guy. Uh, yeah, so I've fixed the swap correctly. Okay. Time capacity often in the worst case, yeah. Nice. So one interview optimization. So it's saying that suppose the input is already open. If algorithm performs every pass even though there is no swap needed, you can optimize it. Okay. So it is saying that we have to optimize it. I think it's trying to check whether it is already swapped. If it is already swapped, there is no need to swap. If it is not swapped, then we have to do swapping. This is a good way to think actually. This actually solves a lot of problems. So let's do this. So this is the bubble zone. So I'll give okay. So first we have to check whether okay. But first what I'm gonna say is it's actually swap. First I'll say SWA is equal to false. This happens. PD becomes true. then I have to break the system. Let's give this and is this makes sense or not. Let's ask this. ChatGPT helps everything, you know. Okay. Okay, so it is saying that problem one is should every pass. Okay, I've initialized it once only. Okay, I think first swap should be placed. I got it. First swap should be placed in the here. Okay, first we should initialize in every should be beginning at every outer loop. So you have did that thing part, right? Then it's also said that breaking in the wrong place. Okay. Okay. So this is also done. Okay. So I think this have to go out. I think this is a perfect. I think this is perfect way to optimize. Let's try. Let's give the code right now. It will definitely help with it. Yes. Let's go. Let's go. So I've optimized the code. So it will check whether it is swapped or not. Where? Oh, nice. Yeah. Okay. I think I'm very happy with bubble sort. I think there is nothing much I have to do in sort, I guess. Let's see
is via
you
that
have told anything interesting.
formula that I showed. There you go, you have it. So that could pretty simple. All in replicating space. But it'd be a very poorly performing algorithm. I also would never use immutability and sorting in the same sense.
Yeah. We have completed the task of bubble sort. I think it is done. Bubble sort is actually done. Let me click on bubble sort is actually done. Now let's do linked list. So we'll do linked list. We're gonna start with that. No, why I'm not starting with selection sort these things? Because I think he did quick sort later on, as you can see. He wrote things later, so we're gonna do with that later on. So let's start with the linked list.
Alright, so
Yeah, we're gonna start with the linked list. We're gonna do that, and Sorry guys for the long break. Sorry guys for the long break. Actually, I was caught up with the work. Hello. Yeah, this was. So, where I was. Yeah, let's go. Where I was caught up. I was caught up in linked list. So I have to start linked list. Okay, let's start linked list. I think there's going to be very less talking. There is more of listening the first class right now, and then I'll start with listening to class. I think it's a good idea. Let's get started.
We're actually on to the second data structure. Is everyone filled with exuberance, joy, happiness? Okay, good. So I did say something weird earlier, of course, which is this statement in JavaScript is not an array. Now we have a pretty solid definition and understanding of an array. Let's see, is this thing an array? It's not an array, right? We can tell it's not an array because you got .push. You can grow it, right? It can grow ad infinitum, right? So something's happening on top of an array minimally. Right, can we at least say that? That there may be an array underneath the hood somewhere, but somehow we have the ability to add, we have the ability to insert, we have the ability to delete from, in which all the indices are actually being adjusted. Because if I shift an array, the first element in the array becomes the 0th element. And so therefore something had to happen, because surely arrays don't offer that. If you delete the 0th element, you null it out, you zero it out, and 1 is still 1, correct? So something is happening. Something more than just an array is happening. Some sort of organizational structure around it is happening. All right, so I'm sure some of you are getting pretty offended by all this talk. Yes, I'm going to say HTML is not a programming language. NeoVim is the greatest editor. Rust is the greatest language, and Linux is the only machine you should develop on. Hot takes for everybody. But let's keep on going. We're going to go to our first real data structure. The reason why I'm calling it the first real one is because arrays just don't feel real in some sense, right? They're so raw, they almost feel like a primitive of computing, right? They don't necessarily feel like they're something. But I mean, there is a lot of things happening underneath the hood. Nonetheless, it still feels very raw. So let's keep on, let's go. I did have this funny joke in here, which is it's available in pretty much every language except for JavaScript. Anyway, so what sucks about an array? Deletion. Well, you can't really delete, right? You can zero out something. Insertion. Well, you can't really insert. You can write. It's ungrowable.
Sorry guys again, small work. Yeah, let's resume it.
Why? Remember Fred. F's in chat for Fred because F went away. So let's talk insertion. Well, it's available in pretty much every language except for JavaScript. Anyway, so what sucks about an array? Deletion. Well, you can't really delete, right? You can zero out something. Insertion. Well, you can't really insert. You can write. It's ungrowable. Why? Remember Fred. F's in chat for Fred because F went away. So let's talk about linked lists. Okay, so this is really our first real data structure. They often call this a node-based data structure. No, not node, as in the runtime for JavaScript, node as in the type of container that will wrap our data. So let's talk about this. This is pretty fun. This is where things I think get really fun, because now we're actually getting into really the heart of the beginning, like the first ventricle, if you will, of data structures. Wow, what an analogy. I'm a doctor practically. All right, so in a linked list, how you can think of it is that if you have a series of values, whoopsies, B, oh, nice writing. What you're going to see is that you're going to see data organized in such a way that you will not only be able to visit, say, this node, it will point to the next node, which means that things like get I obviously work a lot differently, right? You can't just get the ith structure. What would you have to do? Well, if you start here, if this is our head, our first element, we literally have to go, okay, 1, 2, 3. All right, we wanted the fourth item or the third index. There we go. We just got it. We can return out this value. And the reason why I draw circles around this is that it's often a containered item, meaning that you hand me a value t and I put something around it. So that's why I call it a node-based one. So imagine you have a type definition in TypeScript, which is generic over t. What you'd see is a value, which is going to be of type t, and say a next, which could be an undefined value of another node. Oh my goodness. So this was the first algorithm that blew my mind. You can see us allocating and walking memory. I thought this was just like the coolest thing. I hope you feel the same way. This is like the coolest moment in all of my programming career that I can really tangibly remember, is being able to see this in my head and how it worked. And yes, I did see in Java at that point. Please don't make fun of me. But that's just how it was, you know? Everyone's first language is sometimes unimpressive. So there we go. So this is how a linked list fundamentally works, is that you have a node that contains a value and a reference to another value or to another node. And so that way you can walk this daisy chain, if you will, of nodes which contain values. So this would be considered a singly linked list. Why is it considered a singly linked list? Because A points to B, B points to C points to D. You can't walk backwards, right? The moment you go forwards, if you don't have a reference to what is behind you, you've lost it forever, right? It's gone. If I take head and just point it to here, no one's going to be able to access A, right? It's just gone, right? Hopefully, I believe JavaScript's garbage collection is so super advanced, it actually even collect A, because it can tell that though it references data that still is alive, it itself has no references left, therefore dead, right? Now, a doubly linked list usually comes with an additional property, previous node, which means we start getting bidirectional arrows, right? With this, we get the bidirectional nature of a node, which means we can go from A to B and from B back to A, right? We can keep on walking back and forth because we have these links right here. You are referencing the next item. And so often they call this a container, right? Because you, the linked list owner, is going to say, hand it a series of numbers. But it needs the ability to store and organize these numbers within the linked list, so it creates a container to put them into, and then be able to manage it that way. Does that make sense? So instead of using an array, it uses, say, heap allocated objects and puts them. Heap allocated objects, of course, mean objects that are stored in some magical memory place, which is usually more expensive than stack. That's a terrible definition, but go with it. All right, so now let's talk about deletion and insertion. So one cool property about linked lists is that deletion and insertion can be very, very fast. So let's just say we wanted to insert into here F. What would we need to do to insert F? Well, remember, A points to B. So let's make A point to F. F needs to point to A. Remember, because we have a previous and an X, we're doing a doubly linked list. This would obviously be less operations in a singly linked list, but you get the idea. Now we have another problem. B, where does it point to? Points to A. Can't point to A. Just can't, right? We've broken off this link, but we still have this one. So B needs to point to F, and F needs to point to B. At this point, what has happened? We have effectively moved everything over and inserted F. But here's the cool part. What did we have to do? Well, we had to set a bunch of nexts and previouses, right? Like that's it. Are any of those operations based on how many nodes are inside the linked list? No. Are they constant time? Setting next, is that constant? Effectively, right, we can assume that it's constant. You could argue that in TypeScript or in JavaScript, looking up a property on a value could be this under these conditions. Let's just forget all about that and just assume that this is a more traditional style. If you set a piece of memory on an object, it is constant time, right? It's an offset into the object, sets the memory, boom, boom, boom. There we go. So if we set two nexts, right, because we set A's next to be F. Oh, let me write it down here. We say A's to be F's. We set F to be B. Then we have to do the two previously. We do B has to be set to F, and F has to be set to A. All those operations are performed constantly, right? It's just setting a property. Therefore, to insert inside of a linked list at a given position is O of 1, right? Nothing is based on input. No matter how big the value you give me, no matter how many items are in the list, none of that matters. It only matters that I have to break 4 links. And yes, those each can take some amount of time. That's why, like I said, there's always a constant. We drop the constant. It does not matter that there's a constant. Practically speaking, constants can matter, but in this case, it doesn't matter. So there we go. We actually created a doubly linked list, and we were able to insert. So let's think about being able to do the opposite. If we wanted to delete C, we actually created a doubly linked list, and we were able to insert. So let's think about can matter, but in this case, it doesn't matter. So there we go. We actually created a doubly linked list, and we were able to insert. So let's think about being able to do the opposite. If we wanted to delete C, what would we have to do? Okay, we have C. We have C, the node. Let's pretend we got C in some constant time, or we just had access to C. So we're not considering how we got C. We have C, and we want to be able to delete it. So what we're going to have to do is, the first thing we're going to need to do is we're going to go from C to B, back to C, and break that link, right? We don't want to do that. We now have access to B. We're going to have to break the link from B, and we're going to have to point it to C, which points to D, right? We're going to actually have to point through C's next to D, right? So we're going to have to go back, take its next, and point to my current one's next. Do you see? I know. The linked lists are terribly hard to implement, and you often get it wrong your first try, right? So if you think about that, practically speaking, in more kind of code sense, if you had access to C, I'd say C previous equals B, right? B next equals C next. Does that make sense?
Ooh.
Like what I just did there is I broke the link from B that points to C, and I now point it to D. That makes sense, right? I think that makes sense.
Would you put C next, or why not just put D?
Well, the thing is, you have to first get access to D, right? So I'd first have to go like this: D equals C dot next, right? Then I could replace that with D. So that is equally valid as well. But remember, we're now using memory, and we're now playing around with these linked lists. So it does require us to be a lot more specific at all points. So hopefully that sort of makes sense. I mean, this is obviously a very hard concept the first time you see it, but you can see that these next and previouses, you have to be able to manage the links yourself, and that really is just setting where they're pointing to.
So linked list, there's no index. Like you can't.
This question was, in linked list, there's no index. Correct. There is no index. You have access to a node in which you can traverse to get to the node you desire. Now, there's ways to do fast traversal and things like that. We will get to that at some point, but in the current moment, we're just looking at it in a traditional kind of sense. Just a linked list as is. Doubly linked to make it kind of obvious. Singly linked are really easy to implement in comparison to doubly, because doubly you have to do this whole back and forth business. All right, so there we go. So we just set B to point to D, right? So now we need to have D point to B, right? So now notice that the operational order is extremely important, because if I said, hey, C dot next, you're undefined, could we ever access D again? No, D's gone. We can no longer ever access it again. So ordering of operations is extremely important. All right, so then the next thing we'd have to do is D dot previous would have to be C dot previous. right? So now C or D now points to B, right? We just did B to D, D to B. I wish I should have chosen different letters because they're so close. Bravo to Delta, Delta to Bravo. There we go. We now have them together. And so now we need to take Charlie over here. I guess, yeah, wow, DCB. They're terrible letter names here now that I think about it. All right, we're going to take Charlie here, and we can go previous equals
తీసుకుంటాను
సెట్లో
almost. Yes, I got my coffee. I got my coffee with linked list. It's gonna be awesome. It's gonna be awesome. That's it. Yeah. So let's continue.
next equals null, right? We've taken it out of the graph, right? We're deleting C out. So yes, D and B now point to each other. Therefore, C needs to be taken out and no longer point into anything. And at this point, if we want to return the value, we could just simply return, C dot value, right? So there we go. Does this make sense? I tried to kind of break this down into the most fundamental operations. This is a deletion. We can also go over it again with insertion and actually do the writing of the values. We will code this no matter what at some point, but this is the fundamental value right now, or the fundamental operation. Does this all make sense? Is everyone on the same page for the most part? Awesome. All right, so that is a linked list. So again, let's think about the running time of a deletion. Is any of the deleting part right here based on how big your input is?
No.
No. Is it based on how big the value of the node is? No, it's not based on anything. It's based on 4 links. Is 4 a variable or a constant?
Constant.
Confidence right there. Yes, it is a constant. And not only that, is setting next and previous, is that a variable length operation or is that a constant operation? It's a constant operation, right? Because setting something to undefined requires going to the memory and setting it to undefined. Computer's super fast at going to memory. We can just assume it's a constant operation, though it's very, very complex. It's nonetheless very, very constant. And so therefore, deleting is constant time. Just like insertion is constant time. We do the same amount of operations no matter how big or small the list is. Awesome? Hopefully. Now, obviously, if you were really actually programming this, you'd have to put some guards around this, right? If, B is real, then you do the whole next thing. If D is real, then you have to do the previous thing. But in our sweet pseudocode, I will always be dropping undefined checks and things like that, just because it's super hard to be able to write pseudocode and actually write really concrete correct code. So just be okay with things that are like that. Does this all make sense? Are we good with this one? So there you go. This is a linked list.
Yeah, we're gonna do complexity. Before going to this, I want to check for
Now,
the Python.
we've already
So I have to check for the Python because without Python, I need to know how we are doing in the Python. So okay, let's do Python. Okay, let's do with that. Yeah, I've got this. Okay, he's doing this in oops. So I have to go through oops, I guess so. When that is going to be after the zoom insert double linked list. I think we need to know some kind of oops. Oh shit. I think I can cope up. It's easy to understand. Okay. how he's gonna do? Let's
Talked about this, insertion, deletion. And now you can understand that if I were to get a value, I'd have to walk the list, right? So if I ask for the 5th value, there is no way when we have this type of structure right here to get the 5th value. I literally have to write a loop that's going to be like 4, 0 to 5, and current equals current next, right? I'm going to have to walk it until we get to the correct value. Then I can return current's value, correct? We don't return the containing node because then we leak our containing thing and then someone can mess with the next and previous values and boom, our whole list sucks and you lose everything. So always, that's more of a practical implementation standpoint. But you get the idea of a containing node. It's our abstraction for ourselves, not for the outside world. And so in general, getting head or tail, all those things, they can be pretty good operations. So head and tail is a unique get because in the sense that if our linked list implementation has a single reference, head, that points to the first item in the list, getting head can become a constant operation, no matter how big or small the list is. Getting tail can also be a constant operation because, again, we already have a defined pointer to that. It works every single time. All right, so deletion, of course, deletion at the front or the tail, right, the head or the tail, it's actually, again, constant operations, is it not? Because if you think about it, all you have to do is just take this and do the deletion algorithm. Take this, do the deletion algorithm. But if you get in the middle, or you delete in the middle, you have to traverse to that point. So you have a 2 operation cost, the traversal plus the deletion. So deletion from the ends can be constant, but deletion in the middle can be costly if the traversal is costly. But the deletion itself, of course, is not costly. Prepending and appending, constant time, again, because you are able to insert and just break the links from head or tail. So that's very, very fast. But insertion in the middle, it's the traversal, again, that can get you. So long as you can traverse fast, your insertion is fast. So this is kind of like the weakness and strength of a linked list, is that, yeah, it's a bit more complicated. Yes, it's not contiguous memory. There's a whole bunch of computer optimizations about contiguous memory, blah, 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 blah. What matters is that you are able to store these things. The list can be whatever size you want it to be, and deletion from the front or the back are extremely fast. And that is very, very important because there's a lot of structures that you use in which you want to, say, delete the oldest item. The oldest item would be hopefully organized at the tail. Therefore, that's a constant operation. That's very, very fast. All right, so I don't think we're going to implement this just because time is running out, and I think it would take us, it's just a very heavy operation. You saw the next and all the previous's. But in general, this is kind of an interface that you will see if you use that kata program that I built. This is effectively, I believe, the exact interface that would be used in the linked list, which is just like here's all the operations you expect it to be able to do. Now program the underlying operations. All right, let's move forward because we got so many sweet things to take care of. We're going to actually start, I started with linked list because they are the most foundational item. Oh, we do have one question.
I believe the insertion of F after A is arbitrary. You usually will append F either at the beginning or the end of the linked list for constant time.
So the thing is that it just depends on how you're using the list. If you insert at the beginning or the end, you have a constant time guarantee as long as you have a reference to both head and tail, or depending on which side you're inserting on. But if you don't have the reference to the node directly, it's the cost of the traversal to that node, and then it's the cost of the insertion, which is constant. So traversal is where the big thing comes into play here. You have to be able to find or get the node quickly. And there are strategies to do that, and there even is a data structure we're going to go over in which we have constant time traversal and constant time removal. So it'd be fantastic, right? We'll get there. But yes, so in general, I can't tell you how to use a linked list because you use a linked list how you want to use a linked list, but I would strongly recommend not traversing. Anytime you do an end-length algorithm, there's probably a data structure that's better at it, right? That makes usual sense. Sometimes that's as good as it gets, right? But for us, we don't have to worry about that. All right, so why did I start with linked lists? Well, they are super foundational. In fact, they're so foundational, every single linked list is a graph. Every single linked list is technically a tree. You can think of it in these kind of senses, so we will get to these other data structures later, but linked lists are like the most fundamental unit, and long as you understand how to traverse and move around in a linked list, you're going to understand all these other data structures.
Okay.
So we're going to get to the point where we're going to run into, is this an algorithm or is this the data structure? Well, it uses the data structure and then performs an algorithm on top of the data structure. So this becomes a more common theme we're going to see. So is linked list a data structure or an algorithm? Well, you could argue that the insertion is the algorithmic side of it. The actual setup is the data structure itself, right? We can make these arguments, blah, 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 blah. I'm not going to be pedantic. Call it whatever you want. I'm not going to be offended. So our first data structure on top of a linked list is going to be a queue. This is one of the most common data structures I have implemented. I've implemented a queue just this year. I had to shove video down into a video decoder, and the only way to have a buffer to be able to do this and make sure you insert it in the correct order is first in, first out. And what is that? That's a queue, right? And I was using it in C too, so I felt extra, I felt a little bit smarter than everybody else writing C linked lists. It felt very good. So let's go over a queue. So we know what a linked list is now. A queue is just a specific implementation of a linked list. So let's pretend that we have a pointer to head, and we'll do the exact same setup, so that way I can say Bravo, Charlie, and Delta. Let's see, Bravo, Charlie. This is fun. I just decided to do this now. Delta, there we go. So this, of course, is our tail. This, of course, is our head. And so if we want to insert in a queue, well, before we go to that, a queue is simply a FIFO structure, a first in, first out. This is what the Brits call a line, right? And so they call it a queue, we call it a line. That's all it really is. So if we wish to insert into a line, what do you do at a carnival? What do you do at anything? You get into the back of the line. So just like that, if we wanted to insert, say, E, what we're going to do is we're going to have D, we're going to have our current tail point to E. Then we're going to update our tail to point to E. Does that make sense? So it would be kind of a two operation. You could imagine, I'll just write this in actual TypeScript. This dot tail, dot next equals E. Then we just go this dot tail equals E. Does that make sense? We break this link. We are now pointing to the end of the list. Awesome. This makes sense. But a popping operation, we don't pop from the tail. We pop from the head. Now also notice that I'm using a singly linked list. We don't even need a doubly linked list. We don't even need that extra computation time. We don't need that extra property storage requirement. We need very minimal amount of stuff. So a head, if we want to pop it, we do the exact same thing. We would first set head to point to B. So we're doing the reverse operation. Head points to B. We'd save off a reference of head, of course, right? So we'd have some sort of const head equals the current head, right? We point head to B, and then we can just simply take the old one, remove the link, and then return out the value. Now remember, this is a node-based data structure, which means we have a container around the value that you hand the queue. So therefore, we have to do, container a dot value and return that out. So just to write it out, just to be complete, we'd go head equals head. I'm just going to write this out without using this and all that. You can imply this. You can imply const. And then I would do h dot next equals null. And then, of course, whoopsies, we wouldn't want to do that. That is the worst possible operation. We'd want to go head equals head.next. Then set our saved off reference to null, and then just simply return out h.value. Does that make sense? Just simply move it forward, return it. Yeah, see, if I did it the other way around, we'd lose the value, then your whole queue would suck. And there you go, you lose all the values. Don't do that. All right, that's really all a queue is. It's actually shockingly simple because what it's doing is constraining what you can do with a queue. And by constraining what it can do, what kind of performance are you getting out of a queue? When you add to the end, what's the performance? Well, we don't traverse anything, right? We don't go over any sort of list. It's not based on how big of a value you give me. It's simply based on the fact that I have to set one next value to a new node, and I have to update where my tail points to. Those are two constant time operations, right? And creating a node itself is constant time operation in the sense that, yeah, it may require me to go get memory, may require me to go out to the heap and grab memory, but we consider those kind of constant time operations when doing this, and all it requires us to do is just be able to point those new values elsewhere. That's it. So it's a constant time operation. Pushing into a queue is constant. Popping from a queue is the exact same thing, but just in reverse. It's constant. And so, fantastic. We now have reduced what we can do, and we've made sure that it's very, very fast, and it performs a specific algorithm. First in, first out. Is that simple. All right, it's that simple. And so, of course, there's also usually one other operation that comes with queues often, which is peek, the ability to see what is my first element without popping it off. Of course, that would just be, hey, head.value. That's pretty much as straightforward as it gets. And so, of course, I already said this part, we're entering into the world where we constrain things. From here on out, you'll just notice that most things are constrained intentionally, such that we get very good performance out of it. You can only use it in a certain way. Yes, it is technically a generalized linked list underneath the hood, often with a queue, but you can only use it in a certain way. This one is a great one to implement. I think it's fantastic. So we can jump back over to our editor. Remember, if you do have VS Code, I do have a git ignore for everything that starts with a day and some number. So therefore, make sure that you show git ignored files so you can be able to see day one. And we can go down to queue, open it up, and look at this. It's a poorly formatted file. But there you go. We have a class that's generic over T. It has a length that has a number. We have availability for constructor. We have enqueue. So this is typically the phrase that is used when implementing a queue, is to enqueue something is to add it to the queue or push it to the queue. And then we have dequeue, spelled without two UEs, which is always kind of mind-boggling to me, but that one is to remove it from the queue, and of course, peek. So let's figure out first our constructor, and then we can figure out the other methods. So,
Good, pretty good right now. Okay, but what we're gonna do is let's start with doing this like a list stuff, and then let's start with the queue stuff. Okay, I think this is going to be the easiest thing that we could do. Yeah, first to linked list. Let's start linked list. Yeah. Okay. First, before going to ChatGPT, I'll try to do it in. Okay. List. Okay, I can do this traversal, remove, insert, and sort. Okay, traversal. Let me check. Before this, I have to do, I think, oops, which contains classes. So let me check that thing first. I think it's better to do oops first. So what I'm gonna do is let me do the oops. I think it's better to do oops before this linked list stuff, because I think I need to learn classes or something, because for Python I think it's required mostly. So yeah, I'll be doing that. Give me a minute and let's start with the oops. I'll start on how much this is done. I'm almost I think 1 hour 7 minutes ka live is done. What I'm going to do is I'm going to stop this live. I'm going to start a new live which says 2. Let's start with oops so that it's going to be easier. I was just following this guy's front-end master course, so in which he didn't include oops because he's doing it in TypeScript. So for him, I think it's not required. For me, I think it's required. So what I'm gonna do is I'm gonna stop it here. I'm gonna start the new stream in which we're gonna do oops. I think that's good. So I'm gonna stop in this stream. Yeah, let's go.